Radians, arc length and area of a sector. So just a quick history lesson. The Babylonians chose to divide a circle into 360 sections, hence 360 degrees in our circle. However, one theory for the reason that they chose 360 was because it took 360 days for the sun to pass around the earth. So whatever the reason is, this 360 carries no mathematical significance at the moment when we're working with circles or triangles. So therefore, we need something maybe more mathematical that deals with relationships in our circles. And we have something called the radian. And what a radian is the measure of the radius of our circle that is going to be wrapped around the circumference. And what is going to be formed is an angle. And this angle will be called 1 rad. So again, if you were to wrap the measure of the radius along the circumference, you would form an angle. And this angle would be called the radian, or rad for short. So, degrees to radians. How many radians do we have in a circle? Well, if we think about this, our circumference is equal to 2 pi times the radius. So how many radius am I able to place around the circle? Well, obviously, if circumference is equal to 2 pi r, well, the amount of r that I would be able to place would be equal to 2 pi. So there's exactly 2 pi radians on a circle, or 6.28. How many radians are on half a circle? Well, obviously, we would just take half of that value and we would end up with pi. So that means that the radius that we were talking about, each of those forms 1 rad. Now we're able to make some more unit conversions and say that, well, we're beginning with 360 and we know that that would be equivalent to 2 pi rad. 180 would therefore be equivalent to pi rad, and 90 degrees, because it is 1/4 of a circle, would be equivalent to 2 pi divided by 4, which would be equivalent to pi over 2 rad. However, we need a way of converting from degrees to radians for all the other angles in between. And here is your formula. Degrees over 180 would be equivalent to the radians divided by pi. And again, let's just remember that one turn is 360. So let's convert the following to degrees. 3 radians. So in this example, I'm given radians, I need to find degrees. So I use my equation that I showed on the previous slide. X over 180 would be equivalent to 3 divided by pi. A quick cross multiplication and I get 540 over pi. Or if we're looking for the decimal answer, 171.9 degrees. Example number 2. Convert the following to radians. So, to convert to radians, we are using the exact same formula, except that now we are substituting the value of our degrees and we are solving for the value of our radians. So 120 degrees results in an angle of 2 pi over 3 rad, or 2.09 radians. Arc length. So for this arc length, we are basically saying that the angle theta is forming an arc on the circumference of our circle. Whatever the length of this arc is, we would be able to calculate it using this equation, where S represents the arc length, R represents the radius, and theta represents the angle that is formed. Now, theta, it's very important that we keep our measured angle in terms of radians. So if we are given degrees, you need to make the conversion into a radian. So let's start off with a simple arc length question where we are given the radius of 2 centimeters and we are given the angle between the 2 radii, which is pi over 3. So using our formula, S is equal to R theta, we get 2 times pi over 3, which results in 2 pi over 3, or 2.09. Now this would be a very simple type of question. What you would be more likely to see would something that would be a little bit more of a word problem and as soon as I start giving word problems, we know that there's problems that are going to arise with solving it. So in this case, they tell us the radius of curvature of a car racetrack is equal to 200 meters. What is the angle of the car's trajectory if it travels 550 meters? What I would like to see you do is to write down all the information that is given. I would start off by saying the radius is given to me, that is equivalent to 200 meters. I would also be saying that the angle is what I'm looking for, and if the car traveled 550 meters, that would definitely need to be the arc length because I'm on a circular track. Therefore, I would now be able to use my formula, S is equal to R theta, and solve for my angle in radians. And I would get an answer of 2.75 radians. Now we can also calculate the area of the sector that is formed, which is those two radii which are going to enclose an area, in this case the purple area, that is housed by the angle theta, and it's formed by the walls of the circumference of the circle. And we are going to use this equation, area is equal to radius squared times theta, measured in radians, divided by 2. So example number 5 would be a great question that could show up on a quiz or an exam because you need to be able to do everything that I've introduced to you in this lesson. So it tells us the minute hand of the clock is 6 centimeters long. Find the area of the sector formed by the minute hand of the clock in 20 minutes. So the first thing we need to do is we need to say, okay, well, 20 minutes. What is equivalent to 20 minutes? Well, we can do that by sketching our clock. And 20 minutes, because that is 1/3 of an hour, is also 1/3 of 360, which is equivalent to 120 degrees. Given that we have 120 degrees, we now need to make a conversion to get our answer in radians. Why? Well, because we said that we need radians to find the area of our sector. Once we have our angle in radians, we also have the radius. We can use the equation for area, which is radius squared times theta divided by 2. We make a quick substitution in there, so 6 squared times 2 pi over 3, divided by 2, and we get an answer of 12 pi centimeters squared. Do not forget your units, because without units you would be deducted marks. Alright, that's pretty much it for this lesson. I'll see you for the next one.